So today we are going to cover various types of topic, and the slide number is more than 100 pages. So we try to focus on more important slide rather than explaining everything in each slide. Yeah, and today's slide is basically I took many parts from the NUS PhD alumni slide. So yeah, this slides are very great to grasp what's happening in the recommendation system area. So anyway, let's get started. So first of all, I'm talking about the introduction to recommendation system. So how many of you are familiar with recommendation system? Like, have you ever working on it or not today?
Have you worked on the recommendation system before? Any of you want to raise your hand? Yeah. So Hengchang, of course, has.
Okay. Okay, that's great. So then let me cover from the basic things. So when we buy something, let's say I'm going to buy a book, something about the data science. So what we do is we use maybe Amazon or any other e-commerce website. So first of all, what we can do is we use a search function if I know exact book name, or even I don't know exact book name, what it is, but even I can search by using data science term to find a relevant book. This is a search function. But Amazon also provides a recommendation function according to.
Yeah. We didn't share the screen. Sorry.
Oh, yeah.
That's why it's not working. Wait on. When I'm watching the stream, it's actually just showing you. So here's the yeah. Okay, sorry about that, guys. Yeah. Okay, now it makes more sense.
Yeah. Okay, so I'm just showing you some screenshot of Amazon website to find a relevant document. And Amazon also provide a recommendation function. Yeah, I suppose all of you already familiar with it. So basically, Amazon recommend the contents according to the what I opened. I opened data science from scratch book, but Amazon try to propose similar content. This is from same publisher, and these books all of them are associated with data science. So basically, this kind of recommendation is so-called content-based recommendation because they are using a content metadata. For example, they have a publisher's name, and sometimes they can use the author of the book or title or category or any metadata they can use to recommend content, similar contents. Also, Amazon provides other recommendation system, so-called collaborative filtering, CF. This is basically if somebody buy this book, they try to recommend another book which is purchased by same buyer. Yeah, because assumption is that same times of people will buy similar or same books. So it helps to expose more content for end user. So basically, this what we have seen is a search function and the recommendation function from Amazon. But these two functions are quite similar. So information search is we are calling this as a information retrieval. Information retrieval is a information pool from the user side. User write a query to find us relevant content. Then search engine gives the list of contents according to the user's query or any other features that Amazon has. And also, and on the other hand, recommendation is an information push, which means the like for example, Amazon try to push a recommendation list to let user buy other contents. Yeah, these two are very similar concept, but it's a bit different from the through our push perspective. So today we are going to talking about the more like a recommendation side, which is an information push from the publisher. So nowadays, recommendation system is getting very important. So some statistics says that the YouTube, more than 60% of the YouTube content click comes from recommendation, and Netflix more than 80% movie watches comes from the recommendation. So nowadays, we have so many contents in any platform. For example, Netflix. I don't know exact number, but more than hundreds or maybe thousands of contents are existing in Netflix database. But it's hard to find what by myself, as long as I don't know the exact name of contents. So Netflix recommendation help me to find more relevant contents, even I have never seen the name. Yeah, that's powerful function. Yeah, this is a motivation why we study and work on the recommendation engine. Okay, so today we are talking about the more methodology algorithm regarding the recommendation engine. And I don't go to deep dive into the evaluation methods. There are some evaluation methods such as precision recall and DCG, which are in common in this information retrieval evaluation metrics. If you are interested in it, you can check the Stanford lecture note to deep dive into it.
Can you briefly explain the third one? I've
Okay.
heard it a lot.
Yeah.
I think that's NDCG, not SG, right?
Oh,
Can
yes.
I make sure about that?
Cumulative gain.
Cumulative.
Yeah.
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 It's okay.
I think it's
Go ahead.
Okay, so I'm going to explain about the simple model first. So first of all, we need to formulate a problem. So basically, recommendation program is a kind of matching problem. So given the user profile, user ID, my rating history, age, gender, any demographic information, given this user profile, content provider needed to do some kind of matching. So each item has an item ID description, some metadata such as category. So basically recommendation is the try to matching user and the item to making the to maximize the matching. So first of all, this is the most simple one, which is so-called collaborative filtering. Have you heard about the collaborative filtering before? Yeah. Okay, I suppose so, because it's very famous one. So basically, this is a kind of can be formulated as a matrix completion problem. So for example, user Alice watched Titanic and Notting Hill, and Alice also watched Star Wars, and Bob watched Star Wars, and so on. So we have this kind of cross-tabular format data. Then we can convert this data into the rating matrix. Each row representing each user, Alice, Bob, Charlie, and each column is corresponding to contents, Titanic, Notting Hill, Star Wars. And they gave explicit ratings. For example, Alice loves Titanic, so that's why she gave a rating 5 for Titanic, but she doesn't like Star Wars, so and so on. So we have this kind of matrix, and to recommend the contents, we have to impute these missing values. For example, Alice never watched the Star Trek, but if we can compute the, if we can predict a rating for Alice Star Trek, then we can do recommendation according to the predicted rating. That's a problem statement for recommendation engine. Yeah, so there are a couple of ways to do a collaborative filtering. One is to try to find similar items. For example, okay, this is item 4 and this is item 6, and each column corresponding to item and each row corresponding to user. So as you can see, between item 4 and 6, many people give us very similar ratings. So we can consider, okay, these two contents are very similar. Then we can recommend if user like item 4, then we may recommend item 6. This is item similarity. And we can also do same thing for user similarity. So according to this example, user A and C seem to have a very similar preference. So we may recommend contents. For example, user C gave a high rating for item 5, but the user A has not gave a rating to item 2. But since these two user preferences looks very similar, then we can recommend the item 2 for user A. Yeah, that's a high-level concept of collaborative filtering. So we can apply more complex modeling. So as I said, this is basically a matrix completion problem. So we need to impute a missing value to see if predicted rating is high or not. One approach is we can use a singular value decomposition, SVD. So SVD is basically decomposing a matrix. So M is a user rating matrix. So by using a mathematical procedure, we can decompose a matrix M into U and sigma and V. And solving the reason why we do SVD is basically user rating matrix is very sparse because not it's better to do a dimensional reduction. So SVD is one way to do a dimensional reduction to extract essential information out of the very big sparse matrix.
So any comments so far? SVD, everyone comfortable with that? SVD is like one of the highlights of linear algebra, right? So after you take enough linear algebra, you get to SVD and then like, oh, great, everything starts to make sense, right? But then what do you want to take away from SVD? I mean, compared to another technology like PCA, how are PCA and SVD related to each other? Does anyone care to elaborate? Go ahead, yeah.
I think if I remember correctly, the solution to PCA can be given by SVD decomposition. Don't remember exactly how, but
yeah, they're quite closely related, right? Yeah. Any specific comments about PCA versus SVD?
Yeah, I think one solution to, I mean, you can use SVD to give a solution to PCA because in PCA you would find the eigenvalues and eigenvectors. That's what it boils down to in finding the solution. And then to reduce the computation, you can do the same thing by doing SVD because essentially SVD also has eigenvalues and eigenvectors, results in the same thing. So it's more computationally efficient.
Okay, it's more computationally efficient. Are there any guarantees that PCA or SVD has that the other doesn't? For example, with rectangular matrices instead of square one.
SVD usually has, you can do SVD on rectangular matrices, but in PCA, since you are considering the covariance matrix, which usually will be like square, and then you can do SVD on square matrices as well.
Okay. So SVD is one of those techniques that like every data scientist and person in NLP or IR should know. So make sure you have that safely under your belt. Even in NLP, it reoccurs. You've heard of latent semantic analysis, LSA, that is another form of SVD. It's older than what we currently do. Yeah. Okay.
Okay, but there's some problem regarding SVD. SVDs are not best for collaborative filtering. There are mainly two reasons. One is the data sparsity. So when we use a SVD for collaborative filtering, we impute a missing value as 0 to approximate a matrix. But this is not good because the, for example, let's say I never watched Titanic, but I never watched Titanic because I just don't have a chance to watch. But actually, I love a romance story. In that case, if we impute our rating as 0, then result gonna be messed up. And also, when we use a SVD, we have no way to impose a regularization, so it's gonna be overfitting. Yeah, the two main issues when we use a SVD. So to address this issue, matrix factorization is embedded a couple of years ago. So matrix factorization addressed this issue. It's also a similar matrix decomposition approach, but we can change a problem formulation like this. So we okay, maybe it's better to show the figure first. So matrix factorization is basically this is a user ABCD and the contents WXYZ, and we try to predict ranking in the missing combination. So matrix factorization is basically try to decompose rating matrix into two matrices. One is user matrix and the item matrix. We can use the SGD or alternative least square algorithm to deriving these two user matrix and the item matrix. Basically, this for example, we already know these values. So basically, this matrix try to approximate these value while decomposing two matrix. And after approximating the user matrix and item matrix, then once we multiply these two matrix, we can have the real value in the missing combination of the ratings. Yeah, that's a concept of matrix factorization.
Any questions about that? Yeah.
What are the two columns mean for the user matrix?
Yeah, so it's a kind of hyperparameter we can set. It's a so-called the latent features. Yeah, actually we never know which columns mean, but the concept is try to reduce the dimensionality. In this case, we try to reduce dimension to 2. Yeah, technically we can increase 2 or 3 or 4.
So you guys should be comparing this to SVD and PCA, right? In SVD and PCA, you get an approximate matrix of the same size, and then you go cut, right? You say, I just take the top k dimensions, right? And you do it that way. In matrix factorization, you have a loss function, right? So you already set the k ahead of time, right? That is the width of the user matrix and the height of the item matrix, right? They have to be the same, otherwise the multiplication doesn't work out, right? So in SVD and PCA, you're generating the entire matrix and then throwing things away, right? And then in matrix factorization, you're doing it explicitly, right? So you should be able to make parallels with this with deep learning, right? The number of layers or hidden factors is sort of like what you would think of as in a neural network, like the number of dimensions or layers in your neural network. Yeah, Juan?
Can you talk about the formulations in the previous page?
Okay.
So the WUI is the weight of the original matrix, right? So we're trying to do some reconstruction loss here.
Yes. Yeah.
And we only do it on the cell that has the information.
Yes. Yeah. Exactly. Yeah. We only use like knowing information to compute loss function. Yeah. Also, we impose a L2 regularizer, so in order to avoid overfitting.
Why do people use an L2 versus an L1 or elastinate? Anyone want to posit a reason? There are a lot of choices for regularizers, right? Why would you bother with an L2?
One reason is maybe you can tell. One reason is maybe if you want to make your representations very sparse, then you use L1. Because there you are making sure that the length of the vector is, I think, very small. In L2 you are making sure, I mean L2 I think it makes your representations closer to each other in our items. Not sure.
Okay.
I'm just putting.
Do you guys remember the difference between L1 and L2 in the properties?
I think the thing about L2, like a higher size is like sorry, the L1 is like it's a linear loss. So like
Yes.
if you keep it, so the best thing to do is just to drop it, because like it doesn't matter if it goes to one variable or another. So it's best just to select the variable which will give you the smallest loss. Whereas with the L2 is the rate is decreasing. So like it's better to have smaller values, because then if everybody has smaller values, the additional regularization will be smaller.
Okay.
Things are a bit confusing, but
Okay. So hopefully you remember L1 has a preference to select features, right? So it will zero out features if the weight is small enough, or just throw them away, like what we were just saying, right? Like whoever you was just saying. L2 happens to, of course, be Euclidean norm, so it means that it just prefers to have all weights small. So it could be that every feature in your feature vector is being used to calculate. Whereas in L1, it'll say, if your weight is too small, just don't use it. Okay, I assign your weight to someone else. Okay, so you get sparse feature selection with L1. But L2, you probably use every single feature with a small weight. Okay. Why do we use L1 instead of L2? Because L2 is sort of like the most generic type of regularization loss. It doesn't assume much about anything. Okay, and we typically use L2 when the features are homogeneous. They all represent the same thing. So for example, in computer vision, because we're dealing with pixel intensities, all of the things represent pixel intensities. So we can use L2. Okay, when you have a data matrix that has things that represent different things, for example, take your favorite Kaggle competition, which might have like information about age, gender, salary, whatever. Those are categories that are very different in nature. Okay, it doesn't make sense to say, okay, 0.3 of your age difference times 0.5 of your salary or something like that. Okay. So simply we use L1 in those cases because we just say, it doesn't make sense to use a linear combination of all of those, right? So we're just going to zero out some of these and just make a decision based on some parts of the feature space, not all of it. Okay, so that's a very important thing to remember. Like when you read an L2 regularizer, what you should say is, we don't have any a priori information about the data that's going in. We expect it to be pretty uniform. Okay. So that's what you should remember about L2. When you really have no idea, then you might throw an elastic net at it, right? Elastic net means you use L1 and L2. It means that you have absolutely no idea what you're supposed to be doing, and you just try everything anyways, okay? So that's the admission of what I think elastic net is really doing. Okay, so I don't know whether I should use L1 or L2. I just use both at the same time, and I set some like monotonic weighting feature between the two, okay? So you read between the lines when you read papers, right? You say, okay, why are they using this loss function? Is it really based on the principle, or They don't know any better, and they're just throwing terms into the paper to confuse you. So don't write like that if you can. I mean, you should make it clear why you're using a certain regularizer. It's like, oh, it's obvious, right? I don't even need to tell you, right? Okay.
Okay, let's go on. Okay, so this is a kind of high-level illustration of why matrix factorization works. So basically, matrix factorization try to like decompose a matrix, and with the while the reducing a dimension, it's to extract a kind of latent feature. So this approach enable to project users characteristics feature into the certain vector space. Also, in terms of item latent vector, both in terms of item and the user latent vector. So ideally, the purpose of the matrix factorization is to try to project their feature information into the matrix, so that vector space, so that the similar preference users should be close to each other, and the similar item will be like have a similar vector each other. Yeah, that's a high idea for why matrix factorization works. And there's a couple of papers to enhance some matrix factorization approaches. Basically, matrix factorization encodes a user information into some embedding space. We call this is a user-based CL. And also, this paper tried to combine the approaches. So in this factored item similarity model approach, we try to predict the ratings by using a user representation and also using an item rated by user. So which means we try to make a recommendation, but a recommendation is based on the both user representation and the content similarity between the contents which already user rated and contents which user has not already rated. If, for example, if I watch the Titanic, but I never watch other romance movie, but if these two contents are very similar, then we will have a more high ratings theoretically. And also another approach, this is so-called SVD++. Actually, I don't know why this approach called SVD, because I don't think this is the related to SVD, but yeah, anyway, this is a name. So matrix factorization represents a user's user ID and try to project a user space. And a previous approach is the try to combine the embedding of the item information. So this SVD++ approach try to combine these two information. I think this is the type. So this part is not PU, but okay. This is a okay. Sorry, it's not type. So this first term is a user representation vector, and second term is the common as this factored item similarity model approach. So SVD++ is basically try to combine matrix factorization and FISM approach to compute a rating. So so far we have been I'm explaining about how to predict our ratings by using a user watching pattern. But it's better if I can use other features as well, because so far we only use like watching history, but we should have other features such as the user gender, age, or occupation, this kind of user data as well. And also we should have other context of data such as the user's location or user's time or weather or mood or anything. And we should also have some features such as the item category description or any other user metadata should be available. So it's better to it's better to use these features as well, not only just using watching history, like a content consumption history. Okay, so one approach to use other feature could be factorization machines. So okay, let me visualization first. So first of all, explain about the SVD. SVD is basically decompose a matrix into 3 submatrix: user and sigma and item matrix. And the matrix factorization is basically try to decompose the 2 matrix. But factorization machines is it's a kind of different format of formulations. So SVD and matrix factorization, each row is corresponding to one user. This row is user A, this row is user B, and this column is user okay, this column is item A, this column is item B. But factorization machine is a different formulation. So each, for example, let's assume we try to recommend a movie. In that case, if user A watch 3 movies, we should have 3 distinct records instead of aggregating into same line. In this example, user A has a 3 watching record and user B has a 2 watching record and so on. This is a data format for the matrix factorization is going to do. And our purpose is to try to predict a user's preference, such as the user ratings. So this is a target variable what we want to predict. To predict this information, we use these features. For example, this is a training data for model, like this is a user information part. User A watch this Star Wars movie, and also we can concatenate other features such as the other movies ratings that user A already made. We can combine these features into one record to make a prediction. That's the basic idea of the factorization machine. Yeah, so this is a formula to compute the preference score, rating score. So basically, we try to compute one rating score in each user and each content to make a recommendations. So it's a kind of a regression model. We have okay, this is features, and this is a target variable. We transform the data into this format to make a prediction. So each column is corresponding to each feature to make a prediction. So for in this example, we can use some feature like first feature is the is which user, and the second feature is which content, and the third feature is the contents the user had already watched. And we can also use the timing feature when this user watch contents. For example, like if user prefer to watch romance movie at the afternoon, then we should put a high weightage for rating score like that. So by using this formulation, we can use not only watching history, but also use other feature to make a prediction.
So you clear everyone about the difference between FM and MF? Can anyone summarize that for me?
Actually, I think the FM is kind of to take more detailed information, such as, for example, for the user, you consider their age, their gender, their other attributes into this consideration. For example, each two combined attributes can co-affect the results. For example, the 20 years old woman might prefer to buy a bag. It's possible. So the age and gender might affect the result. So that is the core idea of FM. That is take each pair of the two attributes to calculate whether it's calculate the weight of each pair of the two attributes. That's it. I think it's the core idea. Yeah.
Okay. Any other comments? I think if you look at this matrix, it looks much more like the standard supervised learning matrix, right? So you have your label at the end, and you have some humongous feature vector X.
Yes.
Right? And the whole point is that, like Hengchang was saying, is you can make this feature vector as long and as arbitrarily containing any content that you want. And it's put at the same parity level as the information of the user and the item. Here the item is an orange box.
Yeah, so the FM can be solved by the MF metric factorization, and it also can be solved by the neural network ways, such as the NLP. So I will cover it later.
Right. You can look at this as a way to put the CF type of information into a standard feature vectors supervised learning framework, right? Where we are just taking the user and item representation and writing them into a certain column subspace, right? Like Taka was saying, user A is represented by 3 ones for the first 3 instances, which that person classified as 5, 3, and 1 respectively. Okay, so it's more like a transformation of the data, right, into a more like standardized template that we see for supervised machine learning.
I'm just wondering, with this sort of notation, are we just making the sparsity problem worse? And aren't we also making it harder for this? Like, okay, suppose you already have these kind of ratings, it's one thing, but to make the initial rating, like to overcome the cold start, doesn't it make it a bigger problem because half your matrix will just be zeros?
Yes. One solution could be, like, how do I say, transform this original sparse matrix into embedding space. Yeah. My understanding is that these 2 pages are trying to explain about this. Yeah, if I'm not wrong. Like, as you said, original feature matrix is super sparse. So that's why a matrix factorization works, because they try to like create a dense matrix by doing dimensional reduction. So I think we can use this kind of dimensional reduction on the dense vector to other features. Yeah. Yeah, so in this notation Vj and Vi, I think this V means like embedded vector rather than the original sparse matrix vectors.
I think this slide, Shannon was trying to say that FM subsumes a historical approach, right? That FISM is an earlier model, and then FM is equivalent when you only consider the first two item in user column, right? When you only consider the first two columns and you don't admit what we call side information, any other pieces of information that might be relevant to the problem, then FM reduces to factored item similarity model.
Okay, so next I'm explain about the like target variable we can use. There are two types of the target variable or information we can use to build a recommendation engine. One is the using explicit feedback. For example, I can rate Titanic as rating 5 because I love this movie. Yeah, it's a kind of explicit feedback from user, so it's more straightforward to use it. Because if score is high, then it's a strong signal, and and vice versa. But not all in real world, not all system has this kind of system. For example, Netflix they don't use a rating system. Yeah, but even though we can like check out this content or something, but they don't provide a system to give explicit rating from 1 to 5. So I guess they use other metrics, other feedback information to compute to build a recommendation system. It's a so-called implicit feedback. Like for example, if I watch a content or if I click the book or if I purchase shoes or clothes, and then it can be a signal to reveal my preference, and try to use derive some formula to compute some feedback score, implicit feedback score to build a model. That's one of it.
So I'll say that this is one of the most important things that are currently in recommendation systems, because when you browse websites or use an app, you're providing a lot of information, even though you're not explicitly doing any rating, right? So all these implicit feedback is sort of like, the semi-supervised learning compared to supervised learning type of debate that we have in many areas of machine learning, right? So you're getting some supervision, but not direct supervision, right? You're saying, the user has observed this or something like that, right? They scrolled past it or it appeared on their screen. Or in some cases here, the ones that they've written down here are actual sort of explicit indicators that a user actually did, right? So they actually watched the video or they clicked on something or they purchased it. Right, but you can think about all the other implicit information that you could get, right? Like, was it exposed to you in the app? Was it recommended by a friend? Maybe it wasn't still exposed to you, right? All that type of information is usually binary information, and the key part there is it's noisy information. It doesn't provide an endorsement onto that particular thing, but you have there's a weighting or bias that you could induce to say if you were exposed to this, what type of effect does it have on the outcome? Okay, and so this is really helpful because for a lot of data sources, especially for observational data, like say whether you're exposed to an item or not, right? That type of data is much more regular in appearance than rating. Like if you think of yourselves, right? There might be certain platforms where you do a lot of rating and you have established a presence and you continually renew that presence because it's important to you. And other platforms where you're a lurker, you don't do anything, you just observe. But your participation on those two platforms is very different, right? One, you have dense representation. One, you have completely sparse representation. But if you look at observational data, like let's say which things you've seen in your newsfeed, that's sort of independent of whether you act on it or not, right? So that type of implicit data is much more, it has less variability.
Yeah. Okay. Let me give another example. Like for example, like let's say I build a recommendation engine for Netflix. So the okay, as written here, observed interactions don't necessarily positive signal. In that means for example, I watch like a 2 hours movie. No, I try to watch 2 hours movie, but I feel okay. It's not my thing, so I just stop to watch movie less than 5 minutes. Is this a positive signal or negative signal?
Seems to be a negative.
Yes, yeah, absolutely, yes. So, which means the implicit feedback is like it's a bit tricky if you work in the industry because okay. So at least I start to watch the movie, so it can be a signal. But if I stop to watch within 5 minutes, it should be a negative signal. So compared to explicit feedback, implicit feedback is like how to say, like a bit, you need to think, understanding context and domain knowledge to make data into variable. It's very important before deep diving into the complex deep learning or any other models. Yeah. That's my experience in like working, to build a recommendation.
So you're actually building recommendation systems in Word, right?
Yeah. Okay, so then okay, this is another discussion about the how can we set the loss function for building a machine learning model. So what I have been talking about the rating projection to see if users are likely to give a high rating or not. But we also have another type of loss function for ranking. So have you heard about the learning to rank concept? It can be found in the information retrieval context. Yeah, so basically for regression problem, we can like compute some root mean square or this kind of error as a loss function. But we can also set another program statement to as a ranking problem. So this is an example for the ranking prediction problem, but we can set other types of loss functions, so called the ranking loss. So okay, so let's say we build a search engine. So then we need to create a ranking according to certain score. For example, I want to watch the like news Yahoo website, and this is what I want to watch, but I also want to watch some other news website. So there should be ranking. So this ranking loss function is instead of minimizing like a L2 loss of the score, this ranking loss try to like how to say try to impose a machine learning model to give a more accurate ranking result.
Okay, do you guys understand why ranking is more important than the actual score? Okay, so let's give some hypothetical example, right? So let's say you have two systems, all right? One gives you a score for movie A and B as 5 and 4. Another system gives a recommendation but induces or regresses a score of 4 and 3 for the same items. Okay? So one might have a better root mean squared error. Let's say that ground truth is 5 and 4.5. So the first system does better. Okay? But actually, when you think about a recommendation system, most of the time you care about a list-wise or pair-wise ranking. Because when you expose it to the user, you have, this is my top recommendation. This is your second recommendation, right? So the actual score as measured by root mean squared error isn't quite reflective of the use of the recommendation. You care about the ordinal ranking in the recommendation, not the actual score. Okay, so when we use learning to rank, it's another, like Taka said, this is from the 90s or so when we used SVMs and other things to calculate learning to rank. Learning to rank was born from search engine ranking, right? The idea is the same thing. It's like ranking search results, right? And the whole point is you want to rank better things higher up. Okay, that's all right? So it doesn't matter what the score is. It matters that you place A relative to B in the correct position. Okay? If A is supposed to come before B, then you put it there. If you don't, then you have a penalty. And depending on the difference between ranks, okay, the amount of ranks in between, that you would incur more loss. Okay? Just like in a search engine, is it more important to be on rank 1 versus rank 2? Or versus rank 10 versus rank 11. Of course, 1 and 2 make a big difference, right? So when we get to normalized cumulative discounted, which is normalized discounted cumulative gain, NDCG, okay, that's what it's measuring, okay? It's measuring a relative ranking performance, but at saying that top ranks are more important than bottom ranks. So if I score something as like NUS is rank 12 versus rank 13, okay, I get a loss. But if I put MIT in space 1 versus Cambridge, which is supposed to be in rank 1, that's a big difference. You get legal cases against you, right, or whatever, right? It makes big upset news, right? Okay, so those are the types of things that we look for in learning to rank. In learning to rank, we have, I'll just digress for a minute, 3 different loss paradigms that we do for this. Okay, we have point-wise loss, which is what we are doing now, root mean squared error, which means tell me exactly which position you're supposed to put this item. Okay, if it's supposed to be in rank 50, being at rank 49 or rank 51 is a little bit off, but being in rank 30 versus rank 60 for something at 50 is worse. Okay, that's point-wise loss because we consider each individual item. Okay. There's also pairwise loss. It sounds exactly like what it means. It says, for every 2 items on this list, did I put it in the relative ordering? Is A supposed to come before B or B come before A? Okay, I count the number of times these ranking mistakes are made. If I put NUS instead in front of NTU, where the ground truth is NTU is better than NUS, then I suffer a loss. Okay? That's what I mean there. Okay, and there's also the third type, which is list-wise loss. Okay, which means I want to produce the entire list. Okay, anything out of order in that entire list incurs a loss. Okay, so they're all different levels of granularity, and where we're going with this right now is that many of the systems, when you consider a recommendation system, pairwise loss makes a lot of sense. Okay, so you want to induce that. You want to also make sure that the top ranks are accurate. So you favor your loss to say that if you got rank 2 and rank 1 wrong, it counts more than if you got rank 11 and rank 12 wrong. Okay, does that all make sense? All right, so I hope you understand that. That's why you can see all of these parts where you have a positive and a negative prediction subtracted from each other. You're looking at the difference between these 2 values.
Yeah, thanks, Bob. So, yeah, in recommendation context, so not only getting absolute value, but also ranking is important because from user perspective, users see content according to the order of the ranking. So, yeah, some people try to apply this kind of ranking optimization approach. Yeah, even though today's Fatai explains the mostly rating prediction approach. So yeah. Okay.
Okay, then
Okay, let's thank our presenter first.
Having data for some like a final summary stuff. Yeah. But anyway.
Okay, Hengchang, are you going to present from your machine?
yeah, so you need to start
Okay, yeah,
sharing.
we'll stop here on our share.
So it's come to my turn to introduce the deep model and graph-based model for recommendation system. Then Taka also need to give another kind of summarization paper
Okay,
to of yours.
so we'll wait for you to share. That's a very narrow screen you have.
Oh,
Okay, there it is. Okay.
so this is my outline. So since it's 2 o'clock, so I will go through quickly. And firstly, the deep models. Thanks for Taka for introducing what the recommendation system is and some traditional ways such as the MF and SVD. With the neural network be used very popular, so it's very easy to come up with use neural network to deal with some metric stuffs. It's very easy to think about this. So this is one method to use neural network into the recommendation system. That is the representation learning. It's kind of to find some future in the user or items role information such as description, ID, or some others, then get the representation and doing a much methods. So these three papers are very typical model before in 60, 50, and 70 years. And you can see that in 2 or 3 years ago, the interaction learning is very simple, just inner product, that is cosine, the cosine calculation. And the first method of representation learning on the recommendation system, so you can see the representation learning always use the, not always, but usually use the MLP to find the input data's future, to embed it into a vector space. And for input data, you can see that some use the ID. The ID just, you can think is embedding them, so use one hot or kind of like that methods. And some are used the relevant entity. For user, it's the historical items. For item, it's the user group which used it. And I show a very typical model which describes this kind of usage. You can see that the interaction matrix is the interaction matrix between the user and items. So for one row is the vector of user's behavior. You can say that. And one column is an item's interaction record, and send this interaction matrix to two MLP. The first one you can see that's to produce the interaction matrix rows by row, and the second produce this matrix column by column. It's sensible because the first MLP can capture the user's future or a better way to represent them. The second can capture the item's future, then get two kind of representation and finally get the result. It's very simple. And the second can be the interaction function learning. That is kind of like to find a linear relation or non-linear relation by using a neural network. I also list three very typical model here. You can see that here the interaction learning can used by different neural networks the MLP or the CNN. Actually, I don't know why CNN is very useful here, but at least someone have tried for it. The representation learning is just a very simple embedding, probably one hot or probably some other simple embedding from raw data to a vector space. And the input data also, the neighborhood is very usage. That is the basic idea of collaborative filter. That is to find, for user to find the item which their similar user also loved, or item that find the user which their similar item also be used by the usage. And the NCF is this kind of model, which is very famous and also developed by Xiangnan, which also is a group member doing before. It's a very typical example. The first one is the first layer is the input layer, and it contains two vector, the user vector and item vector to describe the user U and item I. In this paper, it's just use one user and one item as the input feature. That is use one hot encoding to transform into a very sparse vector. And the second is an embedding layer. That is a fully connected layer, and to transform a very sparse vector to a relatively dense vector. And secondly is just MLP. Actually, and finally achieve the predicted results, which need to compare with the ground truth results. Actually, the representation learning here can be designed by ourselves, such as the context-aware or content-based, which is content-based is usually a method to solve the cold start problem, and the neighborhood-based ways to build the representation learning. In this paper, it just used a very simple one, just use the ID as the input feature. And but it can, in this paper, it can actually in representation learning, it can use their neighbor. That is, for example, I'm a user. I like the item A, item B, item C. This is my future because it shows my preference. So it's a basic core idea here. So it encodes the neighborhoods. That is for example, for the user, their neighborhoods are what they like or what similar things to it. So encode this kind of future into a vector space. Yeah. So actually, this is future. All of me and Taka talk about is you can think it's kind of like a future based, because all we talk about is about the future stuff. The interaction is future, because what I like, what I choose, what I read is my future, and users' information is future. For example, users' age, users' gender, users' personality, or others is future. And items can be a future. Items, category, description, image, and more complex. There are also some context data, such as in where, that is the location, and where and when, that is the time, and weather, moods, as other things can be taken into consideration in this case. For example, for the user, he rates these items in which time or where. Actually, Taka talked about this before, so I will pass here. But there are another problem need to be considered here. That is, we also talk about how to find the relevance between the different attributes in matrix factorization. Just use matrix decomposition, but in neural network can use other tricks such as attention or such as others. So there are way to actually can very useful for here to find the high order relation between the different attributes or different items. That is the graph structure. Because the graph structure essentially is just a way to build the connection manually before training. That is, you build the edge before you start training. Because in the traditional way, such as the neural network, the MLP, you need to find the relationship. All the work you give this work to the MLP or to the neural network, ask it to find the hidden relationship between the different dimensions. So, but in graph, you can build the edge previously. That is the nodes can propagate the information through the edge. It's more efficient compared to the traditional way. So the goal of network embedding is the goal is to fit an embedding for nodes to build a similarity in the embedding space. Approximate similarity in the original network is very sensible. That is show the representation of each node. The node can be, for example, if there are just two kind of nodes, that is item and user, so the graph can be bipartite graph. If there are three, three-party, triple-party graph. So there are two main components in the application-oriented graph-based model. The two most important things I think need to be taken into consideration is one is the encoder, that is encodes the information and context information to embedding vector, and another is similarity function, that is to find the similarity or relevant scores between each two nodes in the graph. For example, if there is relevance between the two nodes, or if there is core neighborhoods for these two nodes, that is also the main idea of CF. There are lots of different strategies to come out outputs. So so I want to introduce two very useful but simple ways to find the similarity in the graph. One and multi-hop similarity. For take recommendation into consideration, the one hop similarity you can see, for example, I'm user, I rated the item A as 2.5. So there are a score to measure the similarity between me and an item. So one hop similarity, it's very simple, just to fit the loss function that can minimize the output and the ground truth, that is the some scores. That is the score is representation of the edge. And for multi-hop similarity, there is also a very useful way, that is to find the neighborhoods overlap between nodes. That is to find the it's kind of like clustering idea, I think. And there is also kind of another strategy is random word-based similarity, which is also used in Node2Web. Probably some of you I remember are covered in the CNN last week. So it's also can use a random work strategy here. That is to go through the whole graph and then consider it's kind of like you can consider it as a sequential thing, kind of like the text can, which can be used by NLP idea. You can see take the node as a word vector. It's the same. And here I recap some GNN very typical model here, very typical. The GCN, graph GAT, and simple GCN. And this is just a simple recap for what GCN do. It's a neighborhood aggregation process. The key idea is to generate node embedding based on local neighborhoods, and the neighborhood need defined computation graph, and there is also need to be graph passing and information propagation. That is, a node aggregate information from their neighbors through neutral networks. You can see it's very suitable for solving the recommendation problem, because recommendation problem is kind of like to need to find the user's future or the item's futures from their neighbors. So you can see the GCN is very suitable here. So here I want to introduce another passage paper that uses GCN to deal with the CF thing. It's also written by US students, actually in trust group. It's kind the models. It's also kind of representation learning to represent the relevant or similarity between nodes and nodes. For example, in this picture, for example, the U1 like the I4, they do not connect directly, but through some paths, you can find there have some relation or relevance. So the graph network can help it to do this kind of problem. The structure is, I think, can be divided into 3 parts. The first one is embedding layer. It can be constructed by user embedding and item embeddings, include their own informations. And for some traditional methods, for example, the MF and CF, they directly take embedding into fitting iteration. But in this model, it takes the user item interaction graph to propagate the original value to help it can fit the representation better. For the embedding propagation layer, you can see firstly we can think about the one hop situation, one hop case. That is for a connected layer and items. We think the information propagation as the first formulate. You can see that the GCN do not just propagate the information from their neighbors, but it also propagates the information from itself. And the first one is normalization, and this is one propagation step, and the message aggregation is from this is from all of these neighbors, and a higher propagation is kind of like recursive way, that is step by steps from outside to inner side, so you need to define how far you want the information. For example, you need to define step is 3 or 4. Then you need to propagate, find the 4 hop neighborhoods to from out to inside. And second is the model prediction. This model is used concatenating all of different layers as the final as the finals. The presentation at different layer is the advantage is that it can emphasize the message passed over all different connections, and it can have different contribution in reflecting user preference. Okay, that's all. That's my part, and I sort of some resource which I showed before. Probably, if you're interested, probably can help for you. And then turn to Takas. So, if there are any questions,
Yeah, so I think let's first give a hand to Hengchang. But also, I think it's good to reflect a little bit on what Hengchang has presented. So we went from a standard neural network method of calculating embedding, and then to a GCN model that considers neighbors, to a recursive model that considers basically the structure of the entire graph if you run it all the way up to recursion. So do you guys have any comments about what you think about this? Because again, it's good to do some reflection on the models or what types of applications it would be good for. I mean, think about your own recommendations. Not like Huang is working on fake news, for example. Hengchang is working on job recommendation and course recommendation. Some of you are also interested in recommendation or ranking or search result ranking. These are all basically the same fundamental problem, right? You have a bunch of items, you have a particular user profile, and you want to rank items with respect to the relevance to that user.
yeah, because I think a lot of ideas in recommendation system exactly can be used in some NLP problem because it's a very useful idea for some searching engine. If there's some NLP problem, need to find, for example, use the knowledge graph as a context information. Of course, it needs a kind of like search engine. What's the knowledge graph we want, for example? It's actually I think the problems have lots of similarity. So I think it's worth to look into this problem.
Yeah, in fact, if you look at NLP and IR problems, Doug Ward, who's a famous person in IR, said basically there are only 3 types of problems to solve. Okay, like supervised classification, you take an item and you try to classify it somewhere. Alignment problems, like you have 2 sequences and you want to align them together. And selection problems or ranking problems, like the one we're doing now. Selection, you can think of ranking, but with a hard threshold, right? So you just want to say which items are in this list or which are not, or what's the probability of that item being on the list in a certain way, right? So recommendation fits on that agenda, right? You're just saying what's the likelihood or the that an item will be preferred by the user, right? So let me ask you guys, I mean, we have been talking about the matrix factorization approaches, factorization machine approaches, and now graph-based models like GC and then the recursive versions. How important do you think the graph component is for a particular problem? I mean, play it out in your own mind. You take any recommendation problem, let's say, if you use Netflix or Spotify, as a consumer, how important is it to use graph-based modeling to capture what you think is important about your preferences?
Actually, just as I said, the graph model, I think it's kind of like to build a higher order connection before training. Because, for example, if there is no graph structure, it's just use a MLP to deal with the interaction matrix. The MLP don't know which one is very important or relevant with another. MLP don't know. They need to do the SGD or others to fix the function. But in the graph structure, for example, there are edge. So for two nodes, the information can propagate through the edge, but not randomly. So I think it definitely can be more efficient.
What do you guys think?
I think it's born from the assumption of IID.
I don't know what ID is.
The independently and identically distributed.
Okay.
So I mean, if all your users or your items are sampled from common underlying domains, right? Okay. Technically, we cannot assume IID. So it's like so there's the advantage and disadvantage of it. Advantage is that you can exploit the domain informations, right? And then tries to propagate the information within the item. But then there's a disadvantage that it doesn't generalize well. You cannot apply of your offending bounds and of your favorite bounds.
Yeah.
But in our case, then if there's such underlying interaction, then it makes sense to use.
Yeah, that's true.
Can I say something?
Yeah, go ahead, Shenting.
So I think there have been very good points made, but I probably should also. My intuition is that when you talk about, say, as a consumer, let's say when we are watching something on like Netflix, it's not so easy to say that, let's say, Money Heist is a certain genre, or like another show is another genre, and you can just put everything into neat categories. But you have a lot of different interactions in terms of, say, as a consumer, maybe I'm interested in watching movies or shows featuring a particular actor. I may be interested in a particular genre. I might be interested in movies produced by a company. So there's lots of different interactions, and you can't say really neatly categorize them in a like flat table, and that's where I think the graph has an advantage.
Yeah, so I think you're definitely right. You have a lot of metadata or feature data that you want to represent, but there is some latent space that you want to represent better, so that these cross products like Hengchang was mentioning are important. I think the key thing about any type of graph-based approach is similar to the argument why we use RNN or CNN over an MLP, right? Why do we use an MLP?
Yes.
Because we basically don't know what types of connections are important.
Yes,
So we
yes.
just say, well, let's try all of them.
Yeah,
right?
yeah, it's true.
So
Yes.
then you have the problem of over-parameterization, right? Overfitting, because you're going to fit everything, not just the signal, but the noise too.
Yes.
Right? So we're making the observation in the CNN or RNN that either locality or temporal constraints play a big role. We want to emphasize that and tune down the number of parameters so that we can capture signal, right? In a graph-based model, we're saying that there are some latent relationships between items or users that we can observe, and we believe these have a priori importance in making the supervised classification, right? So we're trying to, it's not really feature engineering. It's sort of like feature class engineering. Like you wouldn't say that a part of speech like a determiner or an adjective is a feature. You'd say the whole lump of features that categorize part of speech in NLP is a feature set. So this is exactly what we're doing with graph-based models, right? When we go to the recursive graph-based models and we say, okay, like Hengchang showed a slide earlier, maybe we have more than one layer of recursiveness. You're admitting another model, a higher order model, but of course that adds a bit of complexity. And you have to ask yourself on your own, whether that type of information is going to conclusively be useful to you, right? So I mean, you can think about it in your own Spotify or Netflix. Would you care about these higher order recursive relationships, like a movie or a song that you watched, that you listened to 3 weeks ago, that you listened to because your friend had also watched it because it was in the genre that he liked or something like that. That's the type of recursive structure that you're getting there, right? Do you guys have any comments? You guys are unusually quiet.
I didn't really get, didn't really understand the recursive model. I didn't. Maybe we can talk more about it. I didn't really understand how it applies for this particular case.
In which parts?
Like the last model, I think you're talking about, like, has a recursive nature.
Last model do not have recursive nature actually. It's,
Do you want to put up your slide?
Oh, okay. Oh, you mean this one?
Can you share your screen?
Okay. Okay, sure.
So by recursive model, what we're saying is that an item is described by its neighbors, but the item itself can be described by neighbors where the neighbors themselves are described by items near them.
Yeah.
Right?
Maybe this one.
But all of the graphs are like that, no? Or is it particularly?
This is not a recursive process. It's kind of convolution process. It is from outside to inside to inner side.
Yeah, so this, it's still sort of an iterative, yeah, maybe not completely recursive, but definitely there's some recursion in it because the neighbors of your neighbors are yourselves, right? So there's some idea that you calculate your friend's representation because they're your friend, you are included in their representation, right? And that representation, of course, is coming back to affect your representation. So it's a mutually recursive relationship. But the idea is to spread out the information that you're contextualizing, right?
Yeah.
So that you say, well, Hengchang's tastes are dependent on Guillermo's taste, which are dependent on Huang's taste, which is dependent on Dingshu's taste, etc., all the way around, right?
But like, but all of the all of the graph networks, they operate like that, you know, like for all the models, they operate with this principle in mind. No?
Yeah.
Okay. Just want to check if I. But like with regards because first they present the matrix factorization and the graph. Like I remember that when you talk about graphs, we were talking about decomposing graphs into into matrices. So I'm wondering maybe if there is a lot of similarities there. You know, when you're talking about the spectral nature of the graph, and then we're talking about the factorization approaches. Could they be possibly equivalent somehow, or I would have to think through the maths, but maybe have any of these papers maybe described any equivalence between both methods?
You mean the comparison between the two methods?
Yeah, like mathematically, if they are similar, because when you do because in a sense graph convolution network, you're also decomposing the matrix of item user, because you need to compute you're computing the adjacency matrices and then the weights. And what matrix factorization is doing is basically an adjacency matrix, and you're computing weights. So is it like equivalent weights, or is it like?
I think, for example, in this example, I think match the MF traditional way in factorization decomposition. Probably it cannot find the U1 to I4. I mean, because let me think about it. Because in this way, the U1 do not connect with I4, and I4 do not connect with everything relevant with U1. I suppose so.
I think the easiest way would be to get the user item interactions, right, and multiply with a transpose. You have a user interactions where like the cells will be the similarity between two users. Right? Perhaps we can find some kind of similarity graph.
You mean use kind of two graphs? One graph is to fit the users.
Yeah, user.
Actually, there are some people doing 2 years ago. But it is not efficient if you use these two separately. Actually, it can do at the same time.
Well, I think what's particular about the graphs that in recommendation systems that they're bipartite, like that there's one set of nodes that only connects to another set of nodes. Like we didn't get into the discussion of how the bipartite graphs are affected when we are computing convolutional graph networks. But I think there might be a connection then between both models.
Yes, of course, it's do have the common action, but I don't know how to prove it in perspective. But on general thinking, I think of course if there we build you can see information propagating channel, of course it's more efficient. You can see it is more efficient. Probably you can now see it is more accurately or better, but it is efficient. That's for sure.
Actually, if you look at the user item interaction matrix, right? The idea of using graph convolution, it just basically boils down to having linear combination of different rows, which you know to be similar in some aspect. So it just feels like bringing that aspect of attention into, like, it's just a more elegant way to model the attention. So, I mean, not attention per se, but
relationship.
Yeah.
I think mathematically, all the matrix factorization is dealing with one half proximity, right? Like first order proximity.
Yes.
So you want to go to first, second
I
order,
think
third
so.
order, and convolution.
Yes, I think so.
There's this paper, right? It's stemmed from graph stage.
We can put it on the slide. Then we're also going to turn to Taka's slides to do the last part.
Yes.
Yeah.
Yeah.
So Taka, you can share your screen.
Matrix really probably can also find the linear relationship, but it cannot find non-linear relationship.
In the matrix.
Yeah.
Okay.
Need second order.
I mean, the matrix methods also can also find linear relation. I don't think whether it can find the non-linear relationship in metric computation.
No, that's true. It's like we only have we only have linear operations.
Yes, but in neural network it can find non.
Yeah, but you have like different layers.
Yes.
But yeah, that's true. So it's a little bit like the difference between logistic regression and then multi-layer perceptron.
Yes.
But like you can represent multi-layer, a logistic is a multi-layer. Maybe you can represent a matrix factorization as a one-layer graph convolution network.
Okay, I'm glad we're having a productive discussion, but I also want to make sure we cover the rest of the slides. Taka had prepared 2 sections, so we're going to go to do the last section first because I think it's more interesting for discussion. And I think on Slack there has been some talk from Lucas that maybe we can also think about more industry and other scalable methods for recommendation because that's more interesting for that. But yeah, we'll talk about that another time. Those of you in the room may recall that we may be running a deep recommendation version of this course or reading group, especially with Shanna, since he's an alumnus of this group, but he's also, he's one of the pioneers in this area. So he's in China, but he may be doing a seminar with us next semester. So if you want more recommendation systems detail, you might see that later. But we'll turn it over to Taka now to go through a presentation that he found, or we're going to do another deck from, I forget which university.
I cannot read.
So from Klagenfurt and Milano Polytechnic.
Yeah, so yeah, this year was published last year in Lexis 2019. It was chosen as the best paper in the conference. So it's very suggestive and giving a strong message to us in terms of the recommendation engine for deep learning model. Yeah, let me introduce this paper. So the author is basically so they don't invent a new fancy deep learning model, but what they did is they try to assess the fancy deep learning model published by recently, last 2 or 3 years or so. So the observation is that not only recommendation system, but also in other field of machine learning, deep learning area, like people are academia publishing a paper. Okay, this is the state of the art, and yeah, this is most best model for like NLP or yeah by using BAT or yeah XLNet or something like that. But is this really like making a progress? Yeah, this is a I think this is his motivation to publish this paper for recommendation system. So the purpose of this paper is to evaluate, assess, and in terms of the reproducibility and of the recent deep learning-based recommendation system paper. So author focused on two perspectives. One is the reproducibility. To what extent is recent fancy research in the area reproducible with reasonable effort, without making effort the like 1 month, 2 months, yeah, entire days. Also, second perspective is progress. So to what extent recent algorithm actually giving a better performance can compare to more simple model. Yeah. This is yeah, two main point of this paper. Yeah, so okay, so basically nowadays it's very hard to keep track which is the best model. Yeah, not only I think this is not only problem for recommendation engine, but also yeah, any other area which are exploited by deep learning. So this paper also focus on top end recommendation task, which means the recommendation in system which extract the top, let's say 10 or 20 contents, and to see if like a recall NDCG, yeah, this kind of matrix is better than the basic model. Yeah. So author did a kind of a systematic analysis. So first of all, author did a literature research and found 18 algorithms from the top level research, recommendation research conference. And what they found is that out of 18 algorithms, the author managed to reproduce a result only 7 research papers. So, and to make matter worse, the 6 of them can often be outperformed by the very simple model, such as the nearest neighbor or just linear model. Yeah, that's a bad news for us actually. Yeah, because we spent approx 2 hours to explain like deep learning model and yeah, complex model, but we need to think of it. Okay, so these are conferences that the author researcher paper Lexis, the webconf, KDD, Sigaya, all of them are very notable conference. Yeah. And they took up a long paper from 2018 to 2015 to 18, and they also tried to reproduce the result as much as they could. So approach is if source code is available online, such as the GitHub, they get the source code and they tried to run on their infrastructure on AWS. And if a data set is available on public, they also use it. And if the source code and data are not available, author asks the original writer to give more information to reproduce a result, and they waited for 1 month. Okay, so this is a breakdown of the how many researchers reproduce it by this author. So, yeah, 7 algorithms can be reproduced out of 18. And funny thing is that this research itself reported on the Lexis, but Lexis is the worst one in terms of reproducibility.
But not by a lot. Yeah. I think the acceptance rate at Rex is probably higher than the reproducible rate at Rex. Yeah.
So, but anyway, so at least also managed to rerun the code these 7 algorithms. The CMN, MCLEX, CVAE, blah blah blah. Yeah. So also try to run this algorithm by using a hyperparameter by the original paper. Okay, so this is the difficulty what they found. So they one of the difficulty is this. Yeah, they cannot find a source code, or they refuse to get the information back due to the NDA, or even no reply. Anyway, okay. So also did experimentation. So basically they did very systematically according to the paper. They did a same experimental procedure as the original paper, using same data and the same training text data splitting, and using the same metrics, recall precision or anything. And in terms of hyperparameter, my understanding is that, as far as I read this paper, my understanding is that they try 2 types of hyperparameter. One is the use original hyperparameter written in the original paper. Yeah. And also to compare deep learning model with this simple model, also try to run, attempt to run like simple model like such as k-nearest neighbor. But when they tune the simple model, when they tune the hyperparameter simple model, they use Bayesian hyperparameter optimization research. They try 40 cases in each. Yep. And then these are baseline algorithms that also tries. Like first one is most simple one, just to recommend the popular content in the dataset, top 20 or top 10 or something like that. And also try to use the item k nearest neighbor, like computing a similar content of as I explained earlier. And they also use user KNN and the P3 alpha and RP3 beta. I'm not familiar with these algorithms, but it's a kind of graph-based algorithm, but it's a more way simpler than the deep graph network. Also, they try hybrid algorithm to combine the contents metadata similarity and using like item-based probability filtering. And last one is stream. This is also very simple linear model. Yeah. And okay, so this is a result. Actually, so I couldn't find a detailed explanation of this table in original paper. I can only find it in this deck, but my interpretation is that how many percent of the deep learning algorithm outperforms the simple baseline algorithms. According to this result, for example, this CNN deep learning result, only 30% of comparison, how to say, like deep learning algorithm outperform against the baseline algorithm.
What is 12 then?
Mhm.
What is 12? So the number of
I think the number of the how to say algorithm to use for comparison.
That's the left column is the algorithm is the
Yeah, I think
what is that?
12 means the number of baseline algorithm to compete against this algorithm.
Okay.
Yeah, but actually I'm not 100% sure. Because yeah, this table only appear in this
Also not,
presentation. So.
it's also not reproducible.
Yeah.
We can find a link to the paper and put it on Slack, that we can look at the original paper as well.
So original paper reports each comparison by each algorithm.
or is
Yeah.
or is it the data set?
Maybe we can find more detailed result in the original paper.
Maybe like it reads from left to right. Like each column is like a set of basic algorithms. So CF collaborative.
Yeah.
And then the rows are the algorithms that they're testing.
Yeah.
And then the first column is like the first two algorithms, they didn't pass this test, so they all failed. Then the third row, 4 of 12 of the algorithms in that category pass. And then like, and then the second, and then like as the test gets more complex, only like 3 of the types of algorithms outperforms the baseline. Maybe.
I don't see this table in the original.
Yeah.
You compiled it, I guess, right?
So I just take from this file from the Lexis presentation. Maybe also create it for presentation and the poster session. They didn't put in the original paper.
Okay. Anyways, do you want to go on?
Yes. Yeah. So what we observe is the last deep learning approach at least outperformed these two algorithms in all cases, but still lose against the if baseline model include slim SLIM, which is the linear type kind of linear machine learning modeling. So, and okay, so this is a analysis done by the author. Why this discrepancy happens? Because original paper, okay, so originally these are papers are also insisting that okay, this is the state of the art, or this like achieve a very high like precision or recall or something. But as far as the author tested, they found a discrepancy. So what is that? This is a reasoning. So one is the weak baselines, which means the baseline is not well tuned, or like a baseline algorithm is not good enough. That's what's to assume. So because as I said, the author of this paper, they try to optimize the hyperparameter-based model according to this way. Then they achieve to like win against these algorithms. So the message is the like baseline hyperparameter is not very true. And also found some methodological issues. For example, like I don't know which paper it is, but author says that they found that number of epoch of deep learning model, this parameter is chosen by using testing data. This is not this shouldn't be done, right? Because all of the hyperparameters should be chosen by only using a validation data set. And the testing data should be used only for evaluations. But when this author was going through original code, they found that this kind of the tuning in the original paper written by like these researchers. Yeah. So, and yeah, how can we go move forward? So, yeah, the problem is that it's hard to keep track the which approach is good and even which approach is the statistically significantly better than the baseline method. So he's suggesting to they should like add the more compare against these simple baselines with the well-tuned hyperparameters. And in terms of reproducibility, also like encourage researcher to like publish a code and the data set. Yeah, as much as they could. And also, last thing is the experimental design is important because they happen to find this kind of the invalid tuning. Yeah, that's a brief introduction of this paper.
Okay, comments or things that you guys want to discuss from this? I think this is a little bit more of a meta topic, right? Not specifically recommendations.
I find difficult about recommendation systems like that. At least from personal experience, that like if I use a website that recommends stuff, like I always end up in this like in this box of like bad recommendations, and then I give up or I change then my login. So like in a sense, the recommendation is endogenous to the users who are using it. So like you design an algorithm, and that algorithm will then direct the choices people make in the system, and then you're trying to select, trying to then predict how what people are going to choose, but then maybe a lot of these choices were already determined by an algorithm that was used before, so not inherently from people's preferences or from other things.
It's like the echo chamber.
Yeah, exactly. Yeah. So sometimes I find I don't know how to get around this, both for the quality of the algorithms and for the quality of the recommendations.
There's a lot of work on diversification of recommendations and then temporal sensitivity of recommendations. Both of those are very important topics to mitigate these problems to a certain extent. There aren't a lot of user controls that users know how to interact with recommendation system. That is definitely difficult, right? People doing recommendation systems work also know that the top K baseline is extremely good for certain types of recommendation problems. So sometimes it's very difficult to see a lot of improvement in performance unless you rig your experiments in a certain way. Meaning, for example, you throw out items with less than X number of ratings, or throw out users with X number of ratings, and you can show some. But that tail is huge. I mean, a lot of people casually use systems. They don't have a lot of data. So recommending things in those cases actually is very important. So I don't think A/B testing has come so much to recommendation systems as it is for other things. Like when you consider traffic routing, like Google or Waze traffic, they do have some algorithms that says, okay, will some probability route users slightly differently than the optimal route, right? Because they want to do A/B testing to make sure they don't have congestion.
No, they do.
They
do.
do.
Yeah.
Yeah, they do have it. That's what I'm saying.
No, even for recommendation systems, they do.
They
A
do.
lot of A/B testing.
Okay, good.
Also, maybe one way to go about recommendations like that I haven't seen is like instead of like trying to predict what you want to watch next, is like maybe produce a list of items and then give some reason why you should watch them. You know, like so like then the user, if somebody recommends something to you, you use your own judgment to say I wanna watch this or not. So like so the same way a recommendation system maybe should just give you.
Actually, is one direction of the recommendation system go. It's expandable recommendation system. But usually, I know there is one way to solve this problem is to use the knowledge graph. That is, for example, the two nodes add a knowledge graph to find a reasonable path to go through the path and get another item. So through the path, you can get expandable paths.
Yeah. Oh, nice. Yeah.
Interesting. Okay, so I think today we've hit on just the surface of recommendation systems. There's certainly a lot more to that. But I want to thank all of our presenters today for their and also the scribes for their upcoming work to get things put into the right way. So thanks, Sashankh, for taking off your handwritten notes. So next week we are going to do semantic analysis. Joshi, who's sitting over there, is going to lead the discussion along with Hengchang, I think, and possibly Keng Yi, who's not here. But they may be actually covering a little bit more discourse parsing related work, right? Depending on what their interests are. Okay, so we look forward to seeing you next week. Okay, thanks everyone.